පුතාලා ඇහෙනවද? ඇහෙනවද? hello ළමයි ඇහෙනවද? hello ළමයි ඇහෙනවද? hello
hello sir. hello sir. ඔව් sir.
මේ ඉස්සලා අපි චුට්ටක් විස්තර කතා කරමුද කොරෝනා තත්ත්වෙම කොහොමද ඔය පැතිවල? any news? ඔව් මේ ඒ ළමයා පොසිටිව් නැහැ නේ, හිම දෙයක් නැහැ නේද? පුතාගේ ගෙවල් කොහෙද මේ හසිත නේද කතා කරන්නේ?
තාම රිසල්ට් අවිල්ලා නැහැ sir. sir?
නෑ නේද? හා. හරි වැඩි මේ පරිස්සමින් ඉන්න ඕනේ. ඉතින් දැනට තියෙන සිටුේෂන් එක හැටියට පුතාලා තමන්ගේ මේ පරිස්සම තමන්ම බාර ගන්න ඕන කියන එක තමයි දැන් සිටුේෂන් එකේ තියෙන්නේ. අර social responsibility එක අපි කවුරුත් ගන්න වෙනවා. ඒකයි.
ඔව් සර් දැන් හැමතැනම තියෙනවා.
හැමතැනම තියෙන වෙනාට තාම සමහර මිනිස්සු මාස්ක්වත් දාන්නේ නැහැ. ඒකයි වැඩි.
ඔව් ඒක තමයි සර් වැඩි.
ඔව්. කොහොමද මේ රිස්ක් එකක් තියෙනවා. ඉතින් මේක ඔය කච්චිගේ වයසට නැතත් ඉතින් සමස්තය ගත්තාම ඕකේ අර ස්ට්‍රෙන්ග්ත් එකේ හැටියට වෛරස් එකේ ටිකක් තරුණ කෙනෙක් වුණත් අසනීප වෙන්න පුළුවන්. වයසට ආයෙත් නම් ටිකක් රිස්ක් එක වැඩි. මේ පරිස්සමින් ඉන්න ඕනේ පුතා. මේ කොරෝනා එක හදාගන්නත් බෑ. අනික වෛරස් හදාගෙන ගෙවල් වලට ගියොත් ඉතින් ලොකු ප්‍රශ්නයක් වෙනවා. ස්වයං නිරෝධයනේ හොඳයි. ඒක හරියටම ඔබ්සර්ව් කරන්න 2 weeks. එහෙම නේද පුතාලා?
ඔව්
හරි. අද සිග්නල් වල පොඩි වීක් ගතියක් තියෙනවා. මම මේ මොබිටෙල් ලයින් එකකින් එන්නේ. ඇහෙන්නේ නැත්නම් එහෙනම් පොඩි chat එකක් හරි ඇහෙන්නේ නැහැ කියලා හරි කියන්න. So let's start from yesterday. Hari Buka, thank you. Let's start from last week where we stopped. This is a system. I hope you can see this. So this is expansion of gases. System, the same system, state 1, the entropy level is there S1. At state 2 means the piston moves bit further, S2 intermediate expansions, and S3 further expansion, so that is the state 3. So entropy levels we consider S1, S2 and S3. So as we have understand a bit about entropy, and as we mentioned, entropy is a reflection of some useful energy, but that is not a reflection of thermal energy that is not available for useful work. It's a good portion of energy really, but it's not available for useful work. So that's what entropy reflects. So if this thermal energy unavailable for useful work means it is something a big concern, because we are losing that without using it for useful work. That's why. So as long as at least if we can maintain this entropy level during the expansion, means we are limiting that unavailable of useful work, thermal energy for useful work. So that's why for a base process, S1, S2 and S3 should be the same. If not, S2 is S1 plus a little bit. I put delta S, 1 to 2. S3 is also S2 plus a little increase of S entropy. We call it delta S. So that's why it is very important to minimize this increase of unavailability of thermal energy for useful work. We have to minimize that. Means we have to maintain minimum possible. The most ideal is S3 equals S2 equals S1. That is unchanging entropy. We call this isentropic or constant entropy process. Yeah. So this entropy portion of thermal energy in the system is unavailable. But if that portion, that portion is there at the state 1, that unavailability, so we have to maintain it with letting not to increase the entropy levels. So that is what we call the constant entropy. But that's an ideal case. But in real cases, S1 S2 and S3. S3 would be the largest because with the expansion, your unavailability of thermal energy for useful work also increasing. So that is the point. That is more natural. Yeah, that is more natural. And so I'm going to continue this. I'm going to continue this with one example. I'm going to continue this with one example because with an example, we can understand this better. Okay. Also, before going for the example, if we look into this kind of thing, let's say work isentropic. And when you have work actual, okay, work isentropic is more because you are not generating or you are not increasing the level of entropy. Okay, so W isentropic is ideal. So it delivers a work. Okay, here that ideal work is more than the actual work. That's why when you take the ratio of this W isentropic to W actual to W isentropic. If you take the ratio, this one we call isentropic efficiency. Of expansion over time. Okay, expansion. Interesting, eh? This is quite interesting. Quite interesting, this one. Eh? So this is how it is. Let me put some colors here so that we can clearly see this. But we cannot see the rest. Yeah, very nice. Okay, so this is the situation. So this is the situation. A similar one we can take, a similar one for compression. Okay, for compression, you can take a similar one. That is isentropic compression you imagine air compression or refrigerant compression. So compression, so in actual you need more compression work. In ideal isentropic you need less compression. This is common sense. Yeah. So W compression actual is more than W compression isentropic. That's why again for compression we have isentropic efficiency expression, isentropic efficiency of compression when in this case W actual is of course let me take W isentropic first.
So mic off.
Thank you very much. Thank you very much. So this is the situation for
Excuse me, sir.
yeah, Buddha. Can you hear now? Can you hear now? Hello?
Yes, sir.
Okay, good.
Yes, sir.
Okay, good. So this one, so I will take this way. Later I'm going to email you this, that's why. So this is about compression. Interesting. So W expansion isentropy. Expansion means work done. You know, even in the engine inside, the gas expands and work done. Okay, so W expansion isentropy, that is really the work delivered by the system, is greater than W expansion actual. So isentropic efficiency of expansion is this W expansion actual divided by W expansion isentropy. So the best is isentropic expansion and actual expansion. Okay. So good. So because these things we need some common sense. We need some common sense. Yeah. Very good. So it is like this. So you know what isentropic efficiency means. For expansion means work done. Okay. Work done by the system. Okay. Work done by the system. So compression means work done on the system. Again, Mike or friend, remind me if you are not hearing. So this is W. So in the compression mode, it's the other way. So work done W on the system. Interesting. Yes. Okay. Yeah. So when there is a work done by the system, there should be expansion. Work done on the system, compression means part of the system boundary is moving inward and the gas get compressed. In the expansion, somehow the system boundary moves and the gas, because the gas expands, the boundary moves and the work done from the system or by the system. Okay. So That's how it is. And this work is, we call the mechanical work done because of this expansion and compression. This is we call the mechanical work done. Quite interesting. So you know what isentropic efficiency for compression and isentropic efficiency of expansion. You have some basic idea, and you know what isentropic means. Means you are not letting increasing the unavailable portion of thermal energy for useful work. So not letting increase it means you are getting the best work done out of the system. That's why that is an ideal case. So always you compare it to the real. So when work done by the system, work as expansion isentropic is more than work as expansion actual. When it comes to compression, work compression isentropic is less than work compression actual. Yeah. So then you know the expressions, it's reversing. Compression, you have a ratio, expansion, you have a ratio, and there is a reversing of the ratio. Compression ratio is upside down compared to the expansion ratio. So you will see this. Quite interesting. Quite interesting. Okay. So you feel very good when you see this kind of things. No equations, but the real thermodynamics is working here. Okay, good. Then I have to bring the previous slide back. Yeah. Good. See what I'm going to do. Huh? I want to maintain this as a photographic memory for you. Interesting. Yes, it is here. But don't expect animations anymore. Yes, this one. So, I'm writing an expression for efficiency, neta, isentropic, work done. Okay, neta isen, let's say expansion. So when expansion is there, of course you have 1, 2, and 3 here. But now, in actual, 2 is here. Ideally, you have 2 here. Okay. In actual, your 3 is here. And ideally, you have 3 here. Okay. Yeah, I hope you can understand this. So, ideal. So actual here. This is actual. This is for ideal. Quite interesting. Okay. Let's say this is isentropic expansion. Let's say this is expansion. Let's say this is a turbine work. When it comes to turbine work, W actual divided by W isentropic. Okay. That is equal to, you know, for the turbines, I will explain you later. This is H1 minus H2 actual divided by H1 minus H2 ideal. So I will rewrite it again. So how I rewrite this? Sorry, H1 minus H3. Yeah, this is the final is 3, not 2. But H1 minus H2 also okay, when it comes to the ratio. H1 minus H3, H1 minus H3, ideal. So this one, instead of two, I put 2 dash, I put 3 dash. Okay, so this is H1 minus H3 dash actual. H3 dash actual. H1 minus H3 dash actual. Divided by H1 minus H3 ideal. So now actual, you no need to have the word actual. Here you no need to have the word ideal. Some nice expressions for turbines. Interesting. Good. Okay. Let's say this is ison. So why not I complete it as isentropic? Isentropic. Okay. Very good. Same way. When it comes to compression, okay, when it comes to compression, so I take duplicate of this, I take this out. Compression. Isentropic compression. So this should be compressor work. Okay, compressor work. Actually, isentropic work on compression. Work on compression. Interesting. So that is, so actually smooth. Isentropic is less. That is based on our practical sense or the thermodynamic sense of knowledge. So H1 minus H3 ideal is here. Ideal means isentropic. H1 minus H3 actual is here. So H1 minus H3 divided by H1 minus H3 dash. Quite interesting. Okay. And if I need to draw a compressor here, I can draw it. Yeah. Okay. Gas flow comes, reduce and go out. So your input in, okay, in, output, you can put it here out. This is your one. Okay, it's your one. Yeah, but anything? This is your 3 and 3 dash. Okay, and your intermediate is somewhere in the middle. 2 and 2 dash. intermediate. Quite interesting. Okay, quite interesting. So your work done, W. So instead of this, I put a shaft here. Shaft. Is the shaft work. So your work done is done there. W. Compression. W compression. Quite interesting. Okay. Quite interesting. So this is for compression. Really neat. Simplified one. You can have it here. I believe you can understand this. Okay. This is for compression. Okay. Good. Sorry, that can be done. So that's how it is. So you have basically, you know, isentropic efficiency now. And this H values, how these H values are possible here, we are going to discuss afterward. Yeah. We are going to discuss afterward. These are the open systems of open thermodynamic system. That one we are going to address later. So let's say I'm going to put a question for you. A question for you to understand this. This is the 3.4 tutorial 3 about steady flow energy equation. This is the question. Okay, this is the question. So we have to, I'm going to modify this. Okay, I'm going to modify this before we are working on this. Yeah, let me do the modified one. Right? Let me do the modified one. Before doing this, let me modify this. This is in your notes. Huh? It's in your notes. I take this out. This is the new addition. Yes. So later we will do the original question. Steam enters a turbine operating at steady state of a mass flow rate of 4,600 kilograms per hour. Okay. At the inlet, the pressure is 60 bar. The temperature is 400 degrees Celsius. At the exit, the pressure is 0.1 bar. I take this also out. I take this also out. Oh, it's okay. So this is the question. Later we can make these letters big. Yes. So we will work on this. And this is the question. Now this is the question. So good. So you asked to do this. You asked to do this. I don't know how can you manage this? Can you outline this? Okay. Can you manage or can you outline this? I put if the expansion is isentropic, which means the steam, see, imagine the inlet pressure is 60 bar, is quite high pressure, very high temperature. So then at the exit, the pressure is very low, 0.1 bar, means this high pressure steam expands when this steam passes through the turbine. That's how it is. Okay, when the high pressure, high temperatures energize steam, when this expands, means when this deliver the work, okay, energy level of the steam reduces and finally becomes almost very little amount of energy. That's why you can see pressure is very low. Okay. And also there may be some wetness, means some steam almost converted to water. Water means the steam molecules very silent and joined together and then becomes like water. It is wet steam. That's how when the high pressure steam work done, it's a kind of expansion. At the end of the expansion, your pressure is very low. And also you have lower temperatures, and also that steam may be wet. Okay, that steam may be wet. So if you look into this, okay, let me take from here. Now what happens is this is a turbine. Turbine means it's an expansion, not like this. Okay, it's an expansion. So expansion. In an expansion, so it is something like the volume increases. Okay, and the work is done by the compression. Sorry, by the turbine. W turbine. W turbine. Okay. Work is done. Good. W turbine. It is like this. Okay. So leaving steam is somewhere here. Entering is somewhere here. Okay, entering is somewhere here. So let me add the inlet like this. Okay, so you have the inlet and you have the leaving. See, inlet and leaving outlet. Yes, you're in and out. 3 is here. So, and the middle it is 2. In the middle, 2 and 2 dash. Okay, 2 and 2 dash is in the middle. Sorry, 2 dash and 3 dash. Yes. So our path here is isentropic, means we follow 1, 2, 3. Okay, we follow 1, 2, 3. S1 equals S2 equals S3. This is our path, 1, 2, 3. Not this. So our path is 1, 2, 3. Yeah, good. Yeah, something like that.